Hey, and welcome back to Algebra 1. Our goal for today is what's called prime factorization of monomials, or things that are one big term. Can we break down that one big term into its prime factors? Now remember, factors we looked at when we were looking at our powers. So for example, if we wanted to write the factors of a to the fifth, that would be we would have an a times an a times an a times an a times an a. The factors is just a way of saying, what can I multiply to get the original version? So our goal for today is to get all prime factors of our original item. So we're going to take our original term and break it down to its prime multiplication problem. That's what prime factorization is. You would have done this process in elementary school using what are called factor trees. So our goal for today is that same tool of what are called factor trees, but with more complex monomials or more complex terms than what you would have done when you were in elementary school. So a couple of reminders for prime factorization. Since our goal is to get down to all prime factors, I need to understand what prime means. All right, so we have prime numbers and we have composite numbers. Composite numbers are divisible by other numbers, right? Other numbers go into them evenly, and when we divide them, we get numbers without decimals or remainders left over. Right? Those are your composite numbers, like 4 and 6, right? Those are numbers that we could divide by other numbers and get non-decimal, non-repeating answers. Prime numbers are numbers that are bigger than 1 and only have exactly 2 factors. And those 2 factors are 1 and itself, meaning no other number divides into them evenly without a decimal or a remainder. Things like the number 3 or the number 5. Those are prime numbers because its factors are only 1 and 3 and 1 and 5. So our goal for today is when I'm done, I will have all numbers that are not divisible by any other numbers. I'm breaking down my number into its most basic version of what numbers that are prime multiply to give us the original thing. So our process for today for prime factorization. All right, we want to find 2 numbers that can be multiplied together to get the original number. Right? That starts our factor tree. So our tree is going to have these little branches, and we're looking for any 2 numbers that, if we were to multiply them, give us the thing above it. Now, there's tons of different ways you can do your factor trees. As long as you keep going and breaking down your numbers until you have all prime, you'll get to the same result. Your tree and your branches might look slightly different than somebody else's, but in the end, we should all land on the same exact prime factors for each of our original starting monomials or terms. All right, so check to see if the 2 numbers are prime. If they are not, we continue to break them down. We add 2 more branches until we have all prime numbers left. Our final prime factorization then is our final step. And I'll show you how we go about taking our prime things from our factor tree and writing out our final prime factorization. That's where we'll tend to make mistakes. All right, you're not done until you have prime numbers only. If in your prime factorization you have things that are not prime, you know you're not done, or you made a mistake writing your prime factorization. If you take your prime factorization and you multiply it all the way back out, you better get the original thing you had. If you don't, you know you made a mistake. Don't leave it as your final answer. Run the check. We're breaking down our original thing into what can be multiplied to get us back to that original thing. So do the times in the end. Check your work. See if your prime factorization is correct. I've given you a list of the first 170 prime numbers. I promise I'm not going to ask you to put a bigger than 1013, right? Nothing bigger than 1013 as a prime thing in your tree. You're welcome. All right, so if it's not on this list, keep breaking it down. It's composite. All right, so number 1, we want to break down our number 420 to its prime factorization, or what prime numbers can multiply to get us back to 420. All right, there are a bunch of different ways you could start your tree. For example, 2, right? I would take out a 2 into 10, right? That would be a way to start. If you're not sure where to start, run, guess, and check. Right, take this 420 and start to divide it by numbers. Right, if I take 420 and I divide it by 2, it'll give me the 2 numbers, right? 2 and the 210, right? And then I would say, all right, these 2 things can be 210. Since it ends here in a 0, that tells me a 5 goes into it. It tells me a 10 goes into it, right? So there's a bunch of different things I can do to get started here. All right, if I take 420 and divide it by 10, it's going to give me 42 and 10. All right, if I take 420 and divide it by 5, right, it's going to give me 84 and 5, and so on. As long as you have a combination that when we multiply, it gets us back to the thing above it, you're good. All right, so I'm going to use 10 and 42. All right, but again, we could have used any combination here that when we take these two and multiply, we get the thing that is above it. All right, from here, we have to ask the question of, is that number prime or is it composite? If it's prime, we're done with that part of our tree. If it's composite, we have to add 2 more branches and keep going. So this number 10 is a composite number. So we have to keep breaking it down. All right, so we're going to break it down. 2 numbers we can multiply to get us 10 would be 2 and 5. All right, this number 42 is also a prime number, or composite number. It can still keep getting broken down. So 2 numbers we can multiply to get to 42. 6 and 7. Again, there's other options here for 42. As long as you have any 2 that we can multiply to get back up to 42, you're good. All right, now we got to ask if those numbers are prime or composite. All right, so this number 2 is a prime number. If I'm not quite sure, I go to my list and say, yep, it's right here. It's on that list, so I'm done with it. It's a prime one. I'm stuck with it. All right, it gets a circle around it to indicate it's going to be a number that's part of my prime factorization. All right, this 5 is also a prime number. Again, if I'm confused, go to your list. Here it is, 5. All right, so we say that guy's done. It's going to be a number in my prime factorization. All right, this 6 is not prime. It's composite. Right? Things can multiply to get us there. Right? So we got to keep going. That needs 2 more branches. This 7 is a prime number, if I'm not quite sure. Right? No 6 here. That's why I kept going with it. And here's our 7. All right, so 6, 2 numbers that would get us there is a 2 times 3. All right, we already said that 2 is prime. And if I'm not quite sure about 3, I go back to my list and say, yep, here it is. It's a prime number. It's circle. And now, each individual circle represents a number that I have to multiply to get back up to 420. If it's not a circle number, it's a composite number, and it's not part of my multiplication problem down here for prime factorization, so be careful. All right, now, when I go to write my prime factorization statement, I start with the smallest prime numbers, and I work up to the biggest. All right, so when I'm looking through my circled prime numbers, I have 2 2s, and that's where I would get started. 2 times 2. All right, that eliminates these guys. Then I have a 3, and then a 5, and then a 7. Smallest to biggest. All right, now, from here, we're not quite done. We want to write the best possible prime factorization. So here's the rule. For your number portion of your prime factorization, if you have multiple numbers that are the same, you're going to write them as powers. For your variable part of your prime factorization, you don't do that. And that's where it gets a little bit tricky because we tend to get that rule mixed up in our heads. So be careful. All right, so since I have 2 2s here, I can write it best as 2 squared in my prime factorization. All right, so our final statement here, 2 squared times a 3 times a 5 times a 7. All right, that would be our best version of our prime factorization. Am I right? I'm not sure. I'm going to double check. If I do 2 times 2 times 3 times 5 times 7, or 2 squared times 3 times 5 times 7, and I hit enter, I have to get back up here to 420. If I don't, I know I messed up. I should go back to the branches in my tree and recheck to make sure that I have numbers that are correct. So, for example, maybe I had 10 and like 44 here on accident or something, right? I got to go back and really check to make sure I'm good. I should know if my prime factorization is right or not because I should know if I have prime things, and when I multiply it, it better give me that top number that I started from. All right, let's try another. Number 2. All right, you want to write the prime factorization of 630 c to the 4th q squared. I know this one's a little bit different because we have variables going on here. And so the letter part of this problem is the new portion that we didn't look at in example 1. But we still want to start with the number portion of our tree. So I've started here with our branches. Again, this ends in 0, so we know 10 goes into it. That would be an easy thing to do. Take 630, divide by 10, hit enter. It'll give us this other number over here. Or the shortcut is if it ends in 0, 10 goes in it, and when I cover that, I see a 63. That's the other number. All right, from here, I got to check to see, are those prime things or are they composite? If they're not prime, I have to keep going. All right, hopefully we know 10 is not a prime, right? We can do 2 and 5. Both of those are prime. We looked at those in the previous problem. Now, 63, maybe I'm thinking it's prime. So I go to my chart and I say, all right, here's 59, 61, 62. 63 would be right here. It's not on my list, so I have to keep going with it. All right, for 63, 9 and 7 would be a way we could break it down, right? There are others. 7 was on our list for prime, but 9 is composite. Is the most common composite number that we accidentally circle and call prime because we forget that 9 can get broken down into 3 times 3. All right, now we're done with the number portion. We still have to break down our letter portion, our variable portion here. All right, c to the 4th. We want to get it to its individual factors. So c to the 4th means there are 4 total c's. So I'm going to have 4 branches here that are all c's. That would represent your prime version of your c to the 4th. And then q squared means that we would have 2 total q's, which means I should have 2 q's in my tree. And now we're ready to start building our prime factorization. Smallest numbers to highest first, and then we deal with the letters second. All right, so in our tree, we have a 2, we have 2 3s, a 5, a 7, 4 C's. What is that? I'm going crazy. And 2 Q's. All right, now, on the first example, I said, with your numbers, you can write them better as powers. With your letters, you have to keep them separate. So these C's and Q's have to stay how they are right now. We can only write things over here. The numbers make me better with powers, so be careful. And so we have 2 3s, so we could write that portion of the problem better as 3 squared. So our best possible prime factorization statement, 2 times 3 squared times a 5 times a 7, and then I have to write C, 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 Q, Q. Whew. All right. That would represent our best possible prime values that we multiply to get us back to the original. So run your check. 2 times 3 squared times 5 times 7. When I multiply those, I better get 630. If I don't, I know I made a mistake in my tree. Go back and check your branches. All right, C, 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 C. Would that give me this C to the 4th? Sure would. I'm good. Q times Q. Would that give me this Q squared? Yep. I should know if I got my prime factorization right because I should have all prime things that when I multiply gets me back to that original. All right, number 3. All right, we want to write the prime factorization of 248, a to the 3rd, b squared c. All right, now, this one might not be one that you can, right, there's no 0 here. There's no, like, I know 10 goes into it. It doesn't end in a 5, so I know 5 doesn't go into it. And it has this 248 thing, and I'm not quite sure how to get started. It is an even number, so it might be simple to take this and divide it by 2. And that will give me 2 and the other number. That would be a way to get started. All right, there's a whole bunch of different combinations that work. So 2 and 124 would get you started. That would be an option. Or there are others. So I'm going to use a different one. 8 and 31 would work. But again, 2 and 124, and then I can just keep chipping away. My branches might be different, but my prime things should match no matter how I break it down. All right, from here, I got to think if things are prime or composite. All right, that 31, in my head, I'm saying, I think it might be prime. So I'm going to go to my list. I'm going to just double check. All right, it is right here, so I know it's a prime one. So that one's done. I'm going to stop there. 8's definitely composite, so let's keep going. All right, 2 numbers that would get us to 8 would be 2 and 4, and then 2 numbers to get us to 4 would be 2 and 2. All right, we're done with the number portion of our prime factorization, but we have to do the breaking down of our variables next. We're going to have some more branches over here. A to the 3rd means we would have 3 factors of A. So 1, 2, 3. A. B squared means we would have 2 factors of B. So B and B. And C all by itself, remember that's C to the 1st power, so we really just have 1 C here. All right, we're ready to start building lowest numbers to highest and then variables after that. So 1, 2, 3 twos. 1, 2, 3 twos. A 31. 3 A's, 2 B's, and a C. All right, these have to stay separate. Please don't go back to A to the third, B squared, C to the first. That'd be silly. All right, now the number portion can be written better as powers. So we have 3 2s. So 2 to the third times 31, 3 A's, 2 B's, and a C. And then run your check to see if you are correct. If I did 2 times 2 times 2 times 31, I'd have to get 248. If I didn't get 248, I know I messed up in my branches. Go back and check it. All right, A, would that give me A to the third? Yep. B, would that give me B to the second? Yep. And 1C, would that give me the C to the first? Yes. Run your check when you think you're done. All right, your number 4, go ahead and try this one. 175, R to the third, M, N, P squared. Hit pause here if you need to. Do your tree. Try to get your best possible prime factorization statement. All right, hopefully you did your trees and your prime factorization statement. We should end up here with 5 squared. All right, I'll zoom in a little bit. 5 squared times 7 times 3 R's times an M times an N times 2 P's. Run your check when you're done. 5 times 5 times 7 should give me this 175. R should give me R to the third. Remember, this is an M to the first, N to the first, and the 2 only goes with the P. So if you have M, and N here, that would be the common mistakes because you thought this 2 went with everything. It only goes with everything if it's all grouped together, right? M, N, P to the second is different from M, N, P to the second like this, where this goes to everything in there. So just be careful. I hope this helps you attack your work for today. See you guys later.